Hello, welcome to the lesson on the Pascal's triangle and the binomial expansion. This lesson is going to be more focused on the binomial expansion more than the Pascal's triangle, but just a brief history on the Pascal's triangle. It was Blaise Pascal, a mathematician, somewhere around the 1600s, who is first being credited for this this triangle, and but historically there have been records of Chinese mathematicians probably in the 11th century, and then there have also been Middle Eastern mathematicians, maybe even around 980, who have studied the patterns that emerge from the Pascal's triangle. But it's known by the name of Blaise Pascal's triangle or Pascal's triangle, mainly because maybe it got popular after the 1600s. Now, there are a lot of patterns that emerge in the Pascal's triangle. And as you can see, you actually don't need to memorize the Pascal's triangle. You begin with 1 and 1 and a 1, and you keep on adding diagonal ones, like just adding 1 diagonally. And 1 plus 1 gives you a 2, and 2 plus 1 gives you 3. And if you keep adding the numbers together, right, you can keep generating the triangle, right? So 1 plus 3 is 4, 3 plus 3 is 6, and 4 plus 1 is 1 plus 3 is 4, and so on and so forth. So you can keep adding the numbers and keep generating the values of the Pascal's triangle. So for instance, the next row, you're going to diagonally add a 1 here. So if you were in class, I'd ask you what I would add here. So since I'm recording the video, I'm doing it myself now. So 4 and 1. 4 plus 1 is 5. 4 and 6 is 10. 6 and 4, 10 again, and then 5, and then 1. It turns out that we call this row 5. Okay, so this would be called row 5. Okay, and so if that's row 5, then this is row 4, row 3, row 2, row 1, and this is row 0. Okay, so clearly we're counting from 0 and not from 1. And one good way to recognize this is row 0, or rather row 5, will have 5 on the second term. Okay, row 4 will have a 4 there. Okay, row 3 will have a 3. Okay, and so on and so forth. Okay, so this is what we're going to be using for the binomial expansion. And now, what do we mean by a binomial? A binomial basically has 2 terms, right? For instance, x plus y, or 2x minus 3y, or x squared minus 4x. All of these are binomials because there are 2 terms, right? So that's what we mean by a binomial. And before we move on to the binomial expansion, we kind of need to look at the notation as well. So in the Pascal's triangle, like I already said, we start counting by counting from row 0, right? So that's row 0, row 1, and row 2, and so on. The columns as well, we start counting from 0. For instance, on the 4th row, the first column is called column 0. It's not called column 1, okay? The next column is called column 1, 2, 3, 4, and so on and so forth. So in Pascal's triangle like this, we have a notation. If you want to talk about some particular number, so for instance, if I wanted to highlight, say, this particular value here, okay, I need to give a reference of row and column. So we use a notation, and we use the 6th row. Say, for instance, this is the 4th row, right? And not the 6th row, I'm sorry, the 4th row, and that is row 0, row 1, and that's row 2. So that is 4th row and 2nd column. Okay, remember you're counting from 0 and not counting from 1. Okay, so you always use this notation, row, column. Okay, so for instance, this is fourth row, 0th column, fourth row, first column here, right? And fourth row, second column, fourth row, third column, fourth row, fourth column. Okay. We don't use the row column terminology. We use something called choose, and I'll explain that later at the end of the lesson, why it's called, say, for choose to instead of fourth row, second column. Okay, so for instance, I wouldn't call this fourth row, second column. Okay, I'll call it, say, fourth row, second column. Okay, is written as 4-2, and the value of that is 6. Okay, we also refer to this as 4 choose 2. Okay, or if you're using a calculator, you will see something called 4 choose 2. Okay, so that's what that notation is, and it comes from a chapter of maths where we do systematic counting. So we'll get into that later. I don't want to sidetrack from the lesson. We're just going to assume that this is called 4 choose 2, or we're going to read it as 4 choose 2. Okay, so let's get rid of all this extra bit over here and start looking at some actual values. Okay, now if I wanted to look at 3 choose 2. Okay, so I'm reading this as 3 choose 2, or third row, second column. Okay, so what is 3 choose 2? This is 3 choose 0. This is 3 choose 1. This is 3 choose 2. So 3 choose 2 is 3 over here. Okay, so this value over here is 3 choose 2. Okay, so that is equal to 3. If I wanted to find what is 6 choose 4, I need to figure out where the 6th row is. So this would be row 5. Okay, row 6, we'd start with a 1, go diagonally. And in between the 5 and the 1, you add a 6. In between the 5 and the 10, you add a 15. Okay. And so that is row 0, row 1, row 2, row 3, row 4. Okay, so that value over there is 6 choose 4. Okay, so that value is 6 choose 4. So 6 choose 4 is 15. Okay, so I'm using the word choose. Okay, so for instance, let's write it like this. Is the same as 6 choose 4. Okay, why is it called choose? I'll come and visit that at the end of the lesson. Okay, now we're getting into some notation here. There's a more concise way to write this, but that would require me to introduce something called a sigma notation. So for now, we're going to even skip that, and we're going to write it in a more expanded version. We're not going to be looking at a sigma notation for now. So if I had a plus b to the power of n, the one thing you should not be doing is writing it as a plus b to the power of n is equal to a to the power of n plus b to the power of n. That is wrong, okay? So please do not do that. Okay, you cannot say a plus b to the power of n is a power n plus b power n. Instead, what does that mean? That means a plus b is getting multiplied by itself n times. And that's quite tedious if you actually have to use algebra to keep multiplying a plus b by itself. Maybe you can do it for a plus b square. Maybe you can push yourself to do it for a plus b cubed. But as you keep going to higher orders, that means when n keeps increasing, it becomes very tedious to actually multiply them, okay? So, and collecting like terms. So we're going to look at the expansion using this this formula, right? So we start with whatever the n value is. We're going to start with n choose 0, and that's coming from the Pascal's triangle. And the very first term is a power n. And then b starts with 0. Now the powers of n, right, keep determine what's going to happen and how many terms that are going to be there in this expansion. So for instance, if I had n here, right, this is going to be n choose 0, n choose 1, n choose 2, n choose, that should be n choose 3, right, and n choose, and ultimately it ends at n choose n. Meanwhile, the powers of a, this becomes a power n, the next a is a power n minus 1, a power n minus 2, this should be a to the power of n minus 3, and it goes on until the very last term where a becomes n minus n is 0, so that it just becomes a power 0. On the other hand, the b values keep increasing, right? So it starts with b power 0, goes up to b power 1, goes up to b power 2 next, and then goes up to b power 3, that should be b power 3. Ultimately, it ends at b power n, okay? So that's what I mean by this n determines, right? This n determines where, how many terms are going to be in the series or in the expansion. Now, x plus 3 power 4. Now let's use the formula that we've just written about, okay? So n is equal to 4. We have n is equal to 4. We're going to choose 4 choose 0, and 4 choose 1, 4 choose 2. All of these are going to appear in the formula, right? 4 choose 3. 4 choose 1, 4 choose 0 is always going to be 1. 4 choose 1 is going to be 4. And where am I getting this from? I'm getting this from the Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on and so forth. This is the fourth row. Okay, so this is 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Okay, so those are the values, okay, that we're going to pick out. So 1, 4, 6, 4, and finally we end with 4 choose 4, and that is equal to 1. Okay, so those are the values that we're going to be using the binomial expansion. So let's assemble this together. We start with the n choose 0, right? That's the n choose 0 is where we start with. So we're going to start with 1, okay? We're going to start with 1. A to the power of n. In this case, a is the same as x, okay? So we have, this is your a value, okay? So a value is x, right? So we're going to write that as x to the power of 1, yeah? So x to the power of 4, yeah? A to the power of n. And then we have the b value here, okay? So the b value is 3, yeah? So we're going to write the b value here as 3 to the power of 0. But we know that anything to the power of 0 is 1. Yeah, so we can completely ignore that, okay? The next term, so we have to add a plus sign, okay? Because it's another term. And then is the next part of the binomial expansion, which is n choose 1. N choose 1 is 4 choose 1, and 4 choose 1 is 4. Okay, so we're going to write the 4 from there. And then x to the power of 3, and then 3 to the power of 1, plus the next part in the binomial expansion is n choose 2, which is 4 choose 2, and 4 choose 2 is 6, right? So you're going to put that 6 over there, and then the powers of n keep diminishing, right? The powers of a keeps diminishing, so that's going to be x to the power of 2. The powers of b keep increasing, so now that's going to be 3 to the power of 2. Plus, The next coefficient is n choose 3. So this one comes from here, 4 comes from here, the 6 comes from here, and then the next one is going to be 4. Okay. So we're going to use 4, and then we're going to write x to the power of 1, which is just x, and then 3 to the power of 3, plus 1 multiplied by x to the power of 0, which we know by now is equal to 1. Okay. We don't have to write it. And then 3 to the power of 4. Okay, so as you can see, the powers of b are increasing. It starts with power 0, and then power 1, and then power 2, and power 3, and power 4, and it ends there. Meanwhile, the powers of x keep decreasing. Power 4, power 3, power 2, power 1, and then power 0. Okay? So that is our binomial expansion unsimplified. We're going to simplify that. Okay. Now, so how do we simplify that? Just use exponent rules or index laws. So that's just going to be x power 4. The next term is going to be 4 multiplied by 3. 4 multiplied by 3 is 12. So 12x cubed. Plus, this is 9, right? 9 multiplied by 6 is 54. Okay, so we're going to write this as 54 x squared. Here, 3 cubed is 27. 27 times 4 is 108. Okay, and then we have x plus 3 to the power of 4. 3 to the power of 4 is 3 multiplied by itself 4 times. And that is basically 9 times 9, which is 81. So we have 81 over there. Okay. So that cannot be simplified any further, and that's where we leave it, right? We just, we have, for power 4, right, when n is equal to 4, we have 5 terms. Okay? 1 term, 2 terms, 3 terms, 4 terms, and 5 terms. Okay. For power 4, we'll have 5 terms. Okay, and for power 6, we'll have 7 terms, and so on and so forth. That is a very easy binomial expansion question. It can get a little more complicated, and that's what we're going to do. We're going to take this up a notch and keep adding variations in each and every question. Example 2. This is actually independent practice, so please freeze the screen here and try this out. Okay. So the expansion, the formula is x plus 2 to the power of 3. So going back to the Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay, so these are the values that we're going to pick, 1, 3, 3, 1. Okay, equals. The first coefficient comes from 1. A value is x, and then to the power of 3, and then 2 to the power of 0. Okay, so these are all multiplying each other. And then the next term plus 3, x to the power of 2, 2 to the power of 1, plus the next term is, so you separate each term by a plus sign, plus 3 times x to the power of 1 multiplied by 2 to the power of 2, plus 1 times x to the power of 0. We don't have to write that, right? And then 2 to the power of 3. Okay, so that is your expansion. Okay, so you have, so this becomes equal to 1. Okay, and this is equal to 1. So that's just going to be x cubed plus 6x squared plus 4 times 3 is 12x plus 8. Okay, so that is very similar to what we've just done, but a tad easier because this is meant to be independent practice. Now let's go to questions that have a few variations. Well, before that, let's see what happens, how we could get the same answer if we didn't use the binomial expansion and why we need the binomial expansion. Okay, so without using the Pascal's triangle or without using the binomial formula, okay, how would you do that? X plus 2 multiplied by itself 3 times. Might kind of sound easy at this point. Okay, so you're going to first multiply these two and then multiply these two, right? So x squared plus 2x plus 2x plus 4, and all of that multiplied by x plus 2. So that is x squared plus 4x plus 4 times x plus 2. And again, you multiply this in, okay? So that multiplied by that, and that, and then this multiplied by this, and this, okay? So x times x squared is x cubed, and x times 4x is 4x squared, and then plus 4x plus 2x squared plus 8x plus 8. Collect all the like terms, okay? Collect all the like terms. You have x cubed. Here's a like term, 4x squared and 2x squared becomes 6x squared. And I have 4x, okay, and 8x together becomes 12x plus 8. And voila, that was the exact same answer we got by the binomial expansion using the Pascal's triangle or the binomial expansion formula. X cubed plus 6x squared plus 12x plus 8. Now, if you're wondering, isn't this easier? Yeah, it might be easier for maybe power 2 and 3, but the higher powers you go, it is going to become very, very tedious because you're going to have a lot of terms and you'll have to be collecting like terms a lot, okay? Let's try this one out. If it looks repetitive, please don't get fooled. Each question has a bit of variation from this point onwards, okay? You're welcome to freeze the screen and keep trying it, and you might be able to catch where your errors are, okay? So n is equal to 3, and the coefficients are 1, 3, 3, 1. Okay, so 4 terms. So that is equal to 1 multiplied by 3x to the power of 3, 2 to the power of 0. So you're multiplying all these. The next term is 3 multiplied by 3x squared times 2 to the power of 1 plus 3 multiplied by 3x power 1, and then 2 to the power of 2 plus 1 multiplied by 3x to the power of 0. You don't have to write that. Multiplied by 2 cubed. So let's simplify this. Now this becomes 1, and this becomes 1. Okay, so we don't need those. 3 to the power of 3 times x cubed plus 3 times 9 times x squared times 2 plus 3 times 3 times x times 4 plus 2 cubed is 8. So that is 27x cubed plus 3 times 9, 27, 27 times 2, 54x squared. 3 times 3, 9, 9 times 4, 36, plus 8. Okay, so that is 3x plus 2, the whole cube expanded. The next question. How is this different? We have a negative now. So let's see what happens when we have a negative. So n is equal to 4, and the coefficients therefore would be 1, 4, 6, 4, 1. That is 5 terms. Okay. So that is equal to, start with the coefficient, 1 multiplied by x to the power of 4 multiplied by negative 3 to the power of 0. Okay, because this is nothing but x plus negative 3 to the power of 4. Okay, so from here, sorry, just me trying to allow a little more space here, bear with me. Okay. Okay, that looks better. Plus, the next term starts with a 4 multiplied by x to the power of 3 multiplied by negative 3 to the power of 1 plus 6 multiplied by x to the power of 2 multiplied by negative 3 to the power of 2 plus 4 multiplied by x multiplied by negative 3 to the power of 3 plus 1 multiplied by x to the power of 0 multiplied by negative 3 to the power of 4. Okay. Remember here, I'm doing a multiplication. Okay. So this is a multiplication. That's a multiplication. All these are being multiplied. Okay. So whether you want to use dots or whether you want to use tiny multiplication signs, just remember you're multiplying these terms and then you're multiplying 3 different factors in each term, and then you're adding them term by term. Okay. So the first one is just going to be x power 4. The next is going to be negative 3 times 4, which is negative 12 x cubed. This is going to be equal to 9, right? This is equal to positive 9. So 9 times 6, 54 x squared. And here we have this is equal to negative 27. Yeah, negative 3 cubed is negative 3 multiplied by it, so which is negative 27. Negative 27 times 4, negative 27 times 4 is 108. Okay, so we're going to use negative 108 x. Negative 3 to the power of 4 is negative 3 multiplied by itself 4 times. And that's going to be positive, okay, because you have a negative sitting inside, right? So you have to include the negative, and that is 81, okay? So plus 81. If you can see, we have alternating plus and minus signs, okay? So here is a plus, it's the first term starts with a positive, then a negative, then a positive, then a negative, then a positive, okay? And this will happen every time you have a binomial expansion with a minus sign, okay? Whenever you have a minus sign in a binomial expansion, the terms are going to alternate positive and negative, okay? So why is it called 4 choose 2? Okay, at this point, you're welcome to stop the video and do your homework. But if you're curious, continue to watch on. It's called 4 choose 2 because it comes from counting principles. And let's say I have 4 different objects, okay? I'm going to call these 4 objects creatively A, B, C, and D, okay? Now, if I have to choose only one object out of these 4, okay? So 4, choose one from the 4, okay? Okay, so that is 4, choose 1, which is also called 4, choose 1. And that is, how many different objects do I have? I can either choose A or B or C or D. So I have 4 choices, 4 ways. Okay, that is why 4, choose 1 is 4. Okay, let's try something different. Similar, but little different. If I have to choose 2 objects from 4, okay, that is 4, choose 2. Okay, so how can I choose 2 from the 4 objects A, B, C, D? I could choose AB, or I could choose AC, or I could choose AD, or I could choose BC. Okay, BA is the same as AB, right? BC, or I can choose BD, or I could choose CD. Okay, how many ways is that? Let's count that up. 1, 2, 3, 4, 5, 6. I have 6 different ways. 6 ways or 6 choices. Okay, 6 ways to pick 2 out of 4. Therefore, 4 choose 2 is 6. Okay. Now, what if you had 32 objects and you had to choose 7? Certainly, we are not going to be using drawing the Pascal's triangle up to 32 rows, right? So we're going to use, we can also use a calculator or use the calculator. Most calculators, scientific calculators, will have this, including your TI Inspires. Say a big number, maybe 35, choose 7, or any other number in general, N, choose R, and that is that's the notation you will be seeing later on, probably when you get into grade 11. Okay, so that's why it's called 4 choose 2, or 3, 6 choose 3, or 7 choose 4, or something like that. Okay, and so it's how you choose that. And I think that is quite incredible that you can have objects and you can figure out how many different ways to choose 2 objects from 4 or 3 objects out of 4. And somehow that ties into the Pascal's triangle. Isn't that incredible? No, I think it is. All right, so you can do your homework. And that's the end of this lesson. Tomorrow we'll be doing binomial expansion, but we'll be doing a few harder questions, which involves fractions and which involves probably radicals as well. So that's part 2 of the lesson. Thanks for watching. Bye-bye.